Hi Prof, this is Group 25's video summary on Cassava leaf disease classification. With me are my group mates Glenda, Alicia and William. Cassava plays a vital role in Africa's economy, serving as a staple food and a crucial food security crop. However, viral diseases such as cassava brown streak disease are major sources of poor use. Given the scale of cassava cultivation in Africa, automating disease detection is critical for safeguarding cassava use and supporting food security. This project thus focuses on building a cassava disease classification model using convolutional neural networks to classify cassava images into 4 disease categories or healthy category, where we added an associated label for each class for simplicity. So before we start, let's talk about some challenges we encountered. Firstly, cassava diseases have visually similar symptoms, such as misshaped or discolored leaves. Because of this, traditional image processing methods may not accurately differentiate between healthy and diseased plants. Secondly, our model needed to account for variations in lighting, angles, and plant conditions in rural environments, as these factors can reduce classification accuracy, especially since the dataset images were taken by the farmers' mobile cameras under low bandwidth. Moreover, given the low internet penetration in Africa, our model has to work offline to ensure a wider reach. Lastly, our EDA revealed that some diseases appear less frequently in the dataset, creating a class imbalance that can hinder the model's inability to learn effectively from underrepresented classes. Here we can see that leaves diagnosed with cassava mosaic disease have the highest count. From our research, we noted that the more high-performing CNNs were as follows. By looking through the past winning solutions, we also realized a common pattern in our model architecture. The use of ensemble learning with pre-trained CropNet, EfficientNet, and VIT being the more popular choices. Nearly all submissions stem from this architecture, varying generally in model weights, ensembling techniques, data augmentation methods, and extent of hyperparameter fine-tuning. This finally brings us to a proposed solution. Utilizing machine learning techniques like ensemble learning and weighted self-voting, we use CropNet, then Snake 169, and EfficientNet B4 as core architectures to tackle the classification problem. So to enhance model performance, we also applied the following pre-processing steps. Firstly, we resized all images to 224 times 224 pixels, which is the input shape for our base models. Secondly, pixel values were normalized to a range between 0 and 1 for better convergence, hence improving training stability. Thirdly, the dataset was split into training and validation sets in an 80-20 ratio, using stratified sampling to ensure balanced representation of classes in both sets. As mentioned, we also mapped categorical labels to numerical values for loss function compatibility. Lastly, we did some data augmentation. So we applied transformations like rotation with a height shifting, flipping, shear effect, which is distortion along the x or y axis, and zooming to create varied samples, prevent overfitting, and enhance model robustness by simulating real-world conditions. These are some examples of the resulting images. The configuration is as follows. Firstly, the COMNET used all frozen layers as it was already pre-trained on Cassava data. The same for the nested layer due to computational limitations, and the FisherNet layer had the last 20 layers unfrozen for fine-tuning to the Cassava dataset. Secondly, we implemented early stopping to monitor validation loss and halt training if no improvement is observed within a patient's period of 3 epochs with a minimum delta of 0.001. Thirdly, our models were trained using categorical cross-entropy loss, which is suitable for multi-class classification. We also used add-on optimizer with a learning rate of 0.001 and a batch size of 32 over multiple epochs. Lastly, the final dense snake 169 layer was modified to output 5 classes, the 4 diseases and 1 healthy category, replacing the original 1000 class layer from ImageNet pre-training.
Upon reviewing models and solutions on the competition's discussion page, we found that the CropNet classifier in TensorFlow was widely used, the second place solution also exclusively relying on CropNet. We fine-tuned CropNet, pre-trained on the iNaturalist and plant subset of ImageNet 21K, which contains over 2 million images across 8,864 classes. This broad training allowed the model to capture general visual features before specializing in cassava-specific disease patterns. We implemented the CropNet classifier with the training configurations mentioned by Nanette, using it as a baseline for all future solutions. This approach led to a public score of 88%, placing us in the top 63% of all submissions. To improve the CropNet model, we decided to pass the model through dense layers, essentially using the CropNet classifier as a feature extraction layer. Dense layers are deeply connected with preceding layers and are hence better able to capture complex patterns in the data and learn relationships between different parts of the input. As such, we used 3 dense layers to refine encoded features, before finally passing through an output layer to get the probability for the 5 classes. This helped us achieve a public score of 91%, placing us second. However, the relatively lower private score hinted to us that the model might have overfitted on the public leaderboard data. Therefore, we plan to implement a stacked self-voting ensemble to improve overall accuracy. For that reason, we also implemented two other models. For the DenseNet model, which has been pre-trained on ImageNet, we chose not to unfreeze any layers. We passed the image into the model and then threw a global average pooling layer to reduce the spatial dimensions of the model output and transform it into a 1D vector. Uh, this reduces the output's dimensionality and focuses on capturing only the most important global features of the image. For the efficient net model, we chose to implement this as it was another popular choice among the competition's participants. It is also an efficient and scalable model that is known to achieve high accuracy with fewer parameters. Similarly to DenseNet, we pass this through a global average pooling layer, but this time we also pass it through a dense layer to refine the encoded features. Armed with the three models, we decided to implement soft voting, passing the batch training data into each of the three models, then giving each of the model predictions a weight. Since the CropNet is the best performing model individually, we gave it the highest weight, followed by smaller weights for DenseNet and EfficientNet. Although the smaller weights may seem to imply that these models are insignificant, they play an important role in refining the ensemble. The dense connections in DenseNet promote feature reuse and propagate information across the layers, and the EfficientNet model captures subtle differences in Cassava leaves with high resolution to refine the ensemble. This helped us achieve a public score of 90.9%. After this, we get the self-voting outputs which we input into our meta model. In the meta model, we use stratified k-fold cross-validation to ensure each fold maintains the same proportion of each class label. Since our data is slightly unbalanced, this helps to prevent overfitting, which the logistic regression is sensitive to. For each fold, the meta model receives a weighted soft-voting probability generated by the base models and learns the optimal decision boundaries across the different model predictions, balancing the weaknesses of the base models. The choice for a log regression model is due to its lightweight nature, which is sufficient for this purpose. For log regression, we implemented L2 regularization, which adds a penalty for larger weights and prevents overfitting. After training and evaluating on each fold, we use each fold's trained meta model to independently classify the test images and apply majority voting across these predictions to ensure that the final output is reliable and stable. We achieve a final public score of 90.7%, which may seem insignificant compared to the 88% base model given all the extra work put in, but increased our ranking such that we are now in the top 1%. Our private score also improved significantly, achieving second in the private leaderboard. Showing our model, this shows that our model is far more generalizable and does not overfit on test data, which is why we chose this as our final architecture, although previous experiments got higher on the public leaderboard.
In evaluating our model, we went beyond the Kaggle ranking and incorporated additional metrics for deeper insights and comparison with existing research. Firstly, high accuracy and relatively low log loss across cross-validation folds affirms the model's reliable performance. Secondly, this confusion matrix further reveals that CMD, the most prevalent class, achieved the highest prediction accuracy at 78%. On the other hand, CBB, with fewer samples, had the lowest accuracy. Interestingly, misclassifications were most common between CGM and CMD, with 189 instances, as this is likely influenced by the model's bias towards CMD. These findings underline both the strengths and limitations of our approach. Now, reflecting on the journey of developing the cassava disease classification model, one key insight gained is the critical importance of combining domain-specific expertise with machine learning techniques. Understanding the context and characteristics of these diseases do not only just help design pre-processing steps like data augmentation, but also guide the selection of pre-trained models and architectures. Now, another takeaway is the value of transfer learning in tackling real-world problems with limited data. This approach has helped us to save significant computation resources and improve the model's generalization ability. Additionally, we have learned to appreciate the potential of ensemble learning. Leveraging on the unique advantages of each of the three models, we were able to significantly increase the model's stability across different data sets. Now, moving forward, we can consider implementing advanced sampling strategies like Smoot or Gantt to create a more diverse pool of samples for the more underrepresented classes. Looking forward, hyperparameter optimization through methods like Bayesian optimization can also further improve the model's performance. And lastly, we can also consider exploring integrating explainability techniques like SHAP that will provide deeper insights into model predictions, fostering transparency and trust in real-world applications. Overall, this project has highlighted the potential of machine learning in agriculture and provided valuable lessons on iterative model improvement, setting the stage for future advancement in this field. Thank you.